Hello and welcome. In this video, we're going to look at a couple of practical circuits for our parallel connections. In this case here, we are looking at a house circuit. And so we've got a couple of switches, like our wall switches, that turn on and off the lamps in the house. So we've got two of those back to back here, and those all get fed from this 110 voltage source straight up to this breaker, and this breaker is going to be rated with an amperage value, and you don't want to exceed that amperage value, otherwise it's going to open up, right? And you got to reset your breaker. And that usually happens when we start plugging in too much current into our outlets. Say if you had a clothing iron that pulled 15 amps and a heater that pulled 20 amps, and if this breaker is set for a 30 amp pop, then you will immediately blow the breaker, especially if these two lights are on, because these might only be pulling a couple of amps each. But if you have something else plugged into that parallel circuit, your breaker will stop the flow of current through all of the entire circuit right at the beginning, so you don't break all your components. Right? So we continue down one here. This is a stove circuit. In this case, we have a higher voltage, 120 volts, and we're given multiple pathways. And so here we see our breaker again, so we can stop the circuit completely if our IT increases past the required limit. And on this first circuit here, we see that we have three options to connect to. It's a low, a medium, and a high, but right now it's set to off. Right? So there's no current flowing through there because none of these branches can actually make it to our ground location. The second one has a low setting, which we see has heated up our coil of our stove. And from there we get our 220 volts through our low setting resistor, which means it has a low current through it, which means that this resistor is going to be larger. Right? It's going to be our large resistance to provide that lower current, and that's going to allow this coil here to have less current through it, less heat generated from it. And since this connects all the way to ground, it's going to flow that current through there. This next one gets that 220 volts across the top, but it goes down the middle branch here, which is our medium. That's going to be a medium size resistor. It's going to be slightly smaller than the first one that we looked at for that low branch. And as it comes through here, we see that that generates a higher heat in that coil as it goes to ground. The final one here is going to be our smallest resistor out of all of them because it allows the most current through. Right? We see that that produces the most heat across our coil down here as it connects to ground. Let's do one more. This is a car circuit, right? And so we see the chassis on the ground here. That means that anytime you are going to plug in a wire from your voltage, you're going to run the voltage line all the way back to the battery or the fuse box, and then the ground wire is just going to be bolted directly to the chassis of the car, any metal connection. And that's why we can plug in our battery sources directly onto the chassis of the car right at the battery terminal. Immediately, we take the negative and plug it directly into the metal of the car. And so from there, we can see that across the top here, we have some fuses at the first node. This fuse breaks, then our brakes lights don't work. Right? So if your brake lights stop working, check your fuses. The next thing you would check would be the lamps themselves to see if each bulb broke out independently. And we see that this is a parallel connection here. So those two lights should get the exact same current and should be the same brightness. When you press the brake, it'll close this connection here, turning on the lights. If we continue on, we get to switch a light switch. So if we turn the lights on, then we flow a current through that switch down this branch here, and this is our tail lights. So our tail lights are on if our light switch is on. And we can also have a fuse here that will break before our bulbs do. Right? And we see that these are also in parallel here, so these two lights will be the same brightness, and there's nothing that can shut them off after that. They go directly to ground. So the only thing that can stop that is a light switch at the top and the fuse that's in line with those. Next, we have another fuse here. This fuse will stop the high and low beams from working. So if both of your high and low beams do not work, then you would check this fuse here. And at this point, we would go down towards our low beam lights. Those are also in a parallel connection here, so those should be the same brightness, and those have no other breakage in them to stop the current flow. So you would flip your light switch on to allow current to flow across, and then if they do not work, you would check this fuse right here. Moving forward in the circuit, we see that we have another switch. We can turn on the high beam. So if the light switch is on, the fuse is not broken, and the high beam switch is on, we should have lights coming off. And these two lights are also in parallel, so the right and the left should be the same brightness. There's nothing else to shut them off. They go straight down to the chassis ground. Okay, let us know if you have any questions.